In previous lecture, we have discussed about the basic concept of stress and how is stress different from the pressure. In this lecture, we will discuss about the concept of stress and what are the types of stresses. We have learned that the stress is the internal resisting force per unit area. If this pen is subjected to the expansion forces from here and here, that is the tensile forces, this pen will try to expand. The internal resisting forces will resist the expansion. The internal resisting force per unit area will be called as stress. So stress is resisting force per unit area. Force has a unit of Newton and the area has unit of meter square. So the SI unit of stress will be Newton per meter square. 1 Newton per meter square is called 1 Pascal, that we already discussed. So the 1 Newton per meter square is called 1 Pascal. If the force or stress is big, we will represent it in kilopascals. These all are the units of stresses. The smaller unit is 1 Pascal and 1 Pascal is 1 Newton per meter square. The another unit is 1 kilopascal. 1 kilopascal means 1000 pascals, that is 1000 Newton per meter square. The another bigger unit is 1 megapascal. 1 megapascal is 10 raised power 6 pascals, that is 10 raised power 6 Newton per meter square. Also the 1 megapascal is 1 Newton per mm square, because 10 raised power 3 mm is equal to 1 meter. So it will come here, it will become 10 raised power 3 square will become 10 raised power 6. So 1 megapascal is 10 raised power 6 pascals or 1 Newton per mm square. The another bigger unit is 1 gigapascal. 1 gigapascal is equivalent to 10 raised power 9 pascals, that is 10 raised power 9 Newton per meter square. These all are the units of stress. Now we will discuss about the types of stresses. Stresses are broadly classified into normal stresses and shear stresses. That is normal stress and shear stresses. Normal stresses are those stresses which act perpendicular to the cross section, and the shear stresses are those stresses which act as parallel to the cross section. This is normal stress and this is shear stress. Normal stresses act as normal to the cross section, that is perpendicular to the cross section, act perpendicular to cross section, and shear stresses act as parallel to the cross section, parallel to cross section. Normal stresses are those stresses which act as perpendicular to the cross section, and shear stresses are those stresses which act as parallel to the cross section. Normal stresses can be actual normal stress, it can be bending normal stress, and the shear stresses can be direct shear stress or indirect shear stress. So the normal stress can be actual normal stress, actual normal stress, or it can be bending normal stress. Shear stress can be direct shear stress, or indirect shear stress. Now we will discuss them one by one. First we will take normal stresses and after that we will take shear stresses. नॉर्मल स्ट्रेसेस में सबसे पहले एक्चुअल नॉर्मल स्ट्रेस हम लेंगे. एक्चुअल नॉर्मल stress. Since it is normal stress, it will be perpendicular to the cross section. The actual normal stress, it can be tensile or it can be compressive. It can be both tensile or the compressive. Take a bar, suppose This is a prismatic bar. Prismatic bar is having the constant cross section, and it is subjected to the tensile force. When it is subject to the tensile force, the internal stress will develop to resist this force or elongation. For that, the internal stresses may be developed, and these are called the axial normal stresses. To resist this force, if this is the applied force P, here stresses will be developed, and these stress will be uniform. What is uniform stress? That is, if this is 5 Pascal, this will also be 5 Pascal, this will also be 5 Pascal, and this will also be 5 Pascal. That I mean with the uniform stresses. That's like this. It will be the uniform stress, like this. There is no variation in the stress. It will be constant across all cross section. So there is no maximum value, there is no minimum value, there is a constant value of axial normal stress. So the axial normal stress is has uniform distribution. Here the stress will be load upon area or force upon area. Force is P and area of cross section is A. This stress will be uniform across all the cross section. Here I will mention that axial normal stress is uniform, or it is uniformly distributed. The distribution is important because in the bending stresses we will see the distribution is not uniform. It is the linear distribution in the bending normal stresses. Now the second type of normal stress is bending normal stress. That is bending normal stress. The stresses developed due to the bending are called the bending stresses. Bending stresses are also the normal stresses, just like the axial stresses. Axial stresses are also normal stresses, and bending stresses are also normal stresses. And bending stresses, it can be tensile stresses or compressive stresses. If there is a beam like this, and it is subject to point load, or it is subject to movement like this. It is beam and it is subject to movement like this. It is clockwise movement and it is subject to like this, and it will be bent in the form of this. It will bend in the form of this. If this is the centroidal axis, centroidal axis will be like this. The portion which is above the centroidal axis is subject to the compression. Here it compresses, and the portion which is below the centroidal axis is subject to the tension. Here it is compression because it compresses, and here it expands, so it is tension. And this is called the neutral axis. The material which is above the neutral axis is subject to the compression, and the material which is below the neutral axis is subject to the tension. Here it contracts, and here it expands, so it is subject to the compression and it is subject to the tension. And if we reverse the loads, that is, if the beam is subject to load like this, here the movement is like this. It will be clockwise here, so the movement will be like this, and it will deform like this. Here it is neutral axis and it will be neutral axis. The material which is above the neutral axis is subjected to the tension because it expands, and the material which is below neutral axis is subject to the compression because it contracts. But the neutral axis remains same. That is the later discussion. Here also the neutral axis remains unaffected. The material which is above the neutral axis is subject to the compression here, and it is subject to the tension here. That depends upon the types of loading. Here the material tries to contract, so the internal resistance will be opposite to that. That is, the internal resistance will be tensile stress. Here it tries to expand, so the internal resistance will be opposite to that. That is, the internal resistance will be compressive stress. So here will be tensile stress, here it will be compressive stress. Coming to this, it tries to expand, so the internal resistance will be opposed to that. That is compressive stress. So here it will be compressive stress, and here it will be tensile stress because it tends to contract. So internal resistance will be opposite to contraction. That is, it will be tensile stresses. So bending stress is not subject to the uniform stress. It will be compressive in up to this region, and tensile from this to this region. It is not uniform, as was the case with axial normal stress. Here it will be tensile up to the certain depth and compressive up to the certain depth. Now bending stresses are the stresses that are developed to the bending of the member. Bending stresses may be tensile or compressive. The important to note is that the bending stresses are not uniform, just like the axial normal stresses. These were the uniform stresses, but the bending stresses are not uniform. This is the distribution of bending stress. It is the top fiber, it is neutral axis fiber, and this is the bottom fiber. The stresses at top fiber are maximum, and these stresses reduces to zero at neutral axis and again increases to maximum at bottom fiber. This is the top fiber, this is neutral axis, and this is bottom fiber. The stresses are not uniform throughout the cross section. This is the cross section. The stresses are maximum at outer fiber. Here also it is compression and it is tension, because above neutral axis if it is compression, then it will be tension below the neutral axis, and vice versa. This is the compression stresses, and it will be maximum at outer fiber, and it will be zero at neutral axis. Again, the tensile force will be maximum at outer fiber and zero at the neutral axis. That is the distribution of bending stresses. So the bending stresses are not uniform. These are non-uniform stresses. From calculation, the bending stresses can be computed through bending equation. The bending equation is like, the bending stress is non-uniform, that is the important point. But the bending stress equation is stress divided by y is the extreme fiber से कितनी distance है neutral axis की, that is here to here, the distance between this extreme fiber to this is called the y. So stress divided by y is called m by I is called E by R, where m is applied moment, that is this loading, and I is the moment of inertia of the section. The section is rectangular, so the moment of inertia will be BdQ by 12, and E is the modulus of elasticity of the material, and R is the radius of curvature. It is the bending equation. From bending equation, bending stress is m by I into y. So the bending stress will be m by I into y. Now we will discuss about the shear stresses. Shear stresses act as parallel to the cross section. That we already know that shear stresses are parallel to the cross section and normal stresses are perpendicular to the cross section. If this is the cross section, the shear stress will be parallel to this cross section. Shear stresses act as parallel to the cross section, that is, shear stresses are in the plane of cross section. The shear stresses may be developed due to the due to the torsional loading, or due to the transverse loading, or due to the eccentrical loading. Here it is a bar and it is subject to the transverse loading. This is the transverse loading. The transverse loading will try to bend the beam in the downward direction, but the beam will resist the deformation. It will resist the deformation due to the shear stresses. there will be the development of the stresses which are parallel to the cross section, and these are called the shear stresses. The another example is the shaft. The shaft is subject to the torsional loading. If it is fixed from here and subject to the torsional loading, any point on this will be deformed. Suppose this is the this point A, it will be deformed. If it is subject to the torsion, it will be deformed to the new location, that is A dash. So every point will be deformed to the new position, but the shaft will resist the deformation. It is the deforming force. The resisting force will be opposite to this direction. It is a clockwise direction, so the deforming force will be anti-clockwise direction. This resisting force, which is opposite to this deforming force, is called the, this is the cross section of shaft, and it is subject to the torsion loading like this. The every point on this shaft will be, suppose this point, it will be deformed to this point. Suppose it is A, it will be deformed to A dash, and it is the center. Here is the shear strain. So the torque or the torsion will deform the body, will deform the points from A to A dash. To resist this deformation, the resisting force will be developed, and that will be opposite to the direction of this torsion. Torsion is clockwise, and the resisting force will be anti-clockwise. These are the resisting forces that will be developed to the applied torque. These resisting forces per unit area is called the shear stresses. So the shear stresses are, these are also parallel to the cross section. This is the cross section, and the shear stresses are acting in this plane. These shear stresses are also accompanied by the conjugate shear stresses that we have discussed, that the shear stresses are in conjugate pairs, and the conjugate shear stresses are equal in magnitude but opposite in direction. In order to visualize this, now for better visualization, I have cut the shaft, 1/4 portion of the shaft, and remove it, and it is subject to the torque like this. It will be the torque. The torque will try to deform the cross section, and due to this the internal stresses will be developed. The applied torque is in anti-clockwise direction, and the stresses developed will be in clockwise direction, that is in this direction. These are the stresses developed. Here it will be like this. These are the stresses which are developed and are called the shear stresses. Now these shear stresses are accompanied by the conjugate shear stresses, and that will act in this plane, that is like this. These are the conjugate shear stresses. These are called the longitudinal shear stresses, and these are called the transverse shear stresses, because these are acts in the transverse direction and these acts in the longitudinal direction, because this is the longitudinal axis and these two are transverse axes. The stresses which are acting along the transverse axis are called the transverse shear stresses, and stresses which are acting in the direction of longitudinal axis are called the longitudinal shear stresses. So these are longitudinal shear stresses, and these are transverse shear stresses. Transverse shear stresses. This stress is complementary to this stress, and this stress is complementary to this stress. Suppose take this element, this small element here. This small element is like this. It will be in 3 dimensions. It will be like this. And it is subject to, this stress is transverse stress like this, and it is longitudinal shear stress, and it is like this. These two stresses are complementary to each other. If it is tau xy, it will be tau yx. That I mean with the complementary shear stresses. So these stresses are accompanied by the complementary shear stresses. The complementary shear stresses are equal in magnitude and opposite in sign. If it is 5 Pascal, then it will be minus 5 Pascal. In the two dimensions, it will be reduced to like, if it is 2D planar body, it will be like this. That is, take this cross section. This is the cross section, and upper side it will be subjected like this one, and from right face it will be subject to like this. This is shear stress in xy direction, and that is what we are getting in the books. These type of diagrams are mentioned in the books or represented in the books. The whole concept is like this. So the important concept for the shear stress is the sign convention. How shear stresses are represented, what types of shear stresses are positive, what types of shear stresses are taken as negative, and that will be discussed in the sign convention. Now sign convention for shear stresses, that is sign convention for shear stresses. If this is the planar body like this, and I will mark the two axes, that will be x-axis and this will be y-axis. This is origin, that is 0, 0, and it is the positive x-axis, it is negative x direction, it is positive y direction, and it is negative y direction. It is positive x direction, it is positive y direction, and it is negative y direction. The face which is pointing toward the positive x direction is called the positive face. The face which is pointing toward the negative x direction is called the negative face. The face which is pointing toward the positive y direction is called the positive face. The face which is pointing toward the negative y direction is called the negative face. So this one is positive face, this one is positive face, this one is negative face, this one is negative face. This is the first concept. The second concept is the shear stress which is acting toward the positive direction is positive. The shear stress which is acting toward the negative direction is negative. The shear stress which is acting toward the positive y direction is positive. The shear stress which is acting toward the negative direction is negative shear stress. Here there are two possibilities. This one is the positive phase. I will mention it. It is positive phase, it is positive phase, it is negative phase, and it is negative phase. It is positive phase, it is positive phase, it is negative phase, and it is negative phase. Now the shear stress. There are two possibilities. The shear stress will act like this, or the shear stress will act like this. Only two possibilities are there. Here it will be like this, and it will be like this. Which one will be positive? This one will be positive, or this one will be positive? It will be like it is tau xy, and it will also be tau xy. It will be tau xy, and it will also be tau xy. This is the positive phase, and the shear stress is acting in the positive direction. So phase is positive, and the stresses are acting in the positive direction because it is in positive y direction. It is positive. Positive into positive will be positive. So it will be the positive shear stress. Here it is the positive phase. It is positive phase, and stresses are acting in the negative direction. Positive into negative will be negative. So this is the negative shear stress. So all will be negative shear stresses. Take this example. it is a negative phase and the shear stress is acting in the positive direction, because plus y is, it is negative and positive, it will be negative shear stress. Here it is a negative phase and the shear stress are acting in the positive direction because plus x is. So negative into positive will be negative direction, negative shear stress. Here also it will be, it is the positive phase and the shear stresses are acting in the negative direction. It is minus y direction, so negative direction. Positive into negative will be negative. So the shear, all the shear stresses are negative. You have to check only one. Here if we check the other shear stresses, it will be, it is a positive phase and the stresses are acting in the positive direction. Positive into positive will be positive, so the shear stress will be positive. If you check this one, it is the negative phase and the stresses are acting in the negative direction. Negative into negative will be positive. This is the negative phase and the shear stress are acting in the negative direction. Here it is positive, here it is negative direction. It is positive x direction, it is negative x direction. This is the negative phase and the stresses are acting in the negative direction. Negative and negative will be positive. So this one is the positive shear stress and this one is the negative shear stress. This is the sign convention of shear stress. So this one will be positive and this one will be negative.